Okay, let's start. Any questions from this morning? So for a while we are going to be looking at these fluctuation-induced forces in the Casimir geometry. By which I mean something that is confined between two plates that are at the distance h, so that essentially the interval h, by the boundary conditions, let's say, that are forcing zero fluctuating field, is decoupled from what is happening on the other side. And we are going to explore this in a number of cases. And I remind you what we did last time in the one-dimensional case. We said that the appropriate modes have wave numbers. They're of the form sine n pi over h. If I were to call this coordinate x, going from 0 to h, so that the wave numbers that I'm dealing with are quantized in multiples of pi over h. That if I were to quantize the string that is sitting here, the corresponding frequencies would be related to these wave numbers through some kind of a speed, and that the ground state energy E0 is going to be a sum over all of these modes of the 0-point energy of the oscillator, which is h bar omega over 2, which then converts this into h bar c over 2. From here I will have pi over h and a sum over n of 1, which we said really encodes a divergent part, which is divergent because we didn't put a short distance cutoff in the system to make it finite. If we were to make it, put the short distance cutoff, then this infinity would be related to the size of that cutoff, but it is unrelated to calculating the forces if I were to move the separation h, because whatever force per unit length I gain or lose from this side is compensated by the other side. So really what I need to do is to figure out a part that is finite. And there's various ways of doing that. In particular, by regarding this as a zeta function, we find that this value is minus 1/2. Once we've calculated that, we can calculate the force, which is minus dE by dH, which comes out to be minus h bar c over h squared, and the coefficient, which is pi over 4. Unless I made a mistake, which I don't think I did. Some other? There was a question? Oh, sum of, yes. Sum of n, which is zeta of. And the answer, that's the answer. Okay, so it is sum of n, because all of these things are proportional to n. Good, so people are keeping attention, which means that this is zeta of 1, which is not 1/2, but 1/12, which means that the final answer here will be 1/24, which kind of makes more sense. Yes. Yes. Okay. So if I were to introduce some kind of a cutoff, I will actually get indeed an infinite part that is proportional to h, but also in this case we'll have a cutoff dependence also. Okay. The part that it is proportional to h indeed, because it's the energy per unit, is going to be essentially the energy content of these 0-point fluctuations. Yes. Okay, fine. So now I'm going to go step by step to the case of D equals to 2, but thermal, which means that I'm going to something that, again, I won't have a physical realization for. Imagine that I have a fluctuating field. At 0 and h, I have my phi equals to 0. And in between, the cost of fluctuations is proportional to gradient of phi squared. And I have to calculate a classical partition function. So up to various factors of beta, z is going to be proportional to the functional integral of d2x gradient of phi squared with a factor of k over 2. It doesn't matter. When I go to Fourier space, this becomes integral over phi tilde of q e to the I guess let's write it in this fashion, product over modes that I now can treat independently. The probability for each mode is k over 2q squared phi tilde of q squared. And this basically gives me a product over all the modes of factors of root 2 pi k q squared. Okay, now in this case, modes along this direction can have any wave number that I'm going to indicate by scalar q, but in this direction they have to be quantized to be n pi over h. Right? So essentially, this is really a sum that involves this q and n. So that when I want to calculate log z, given that I have an interval of size h, what I need to do is to sum over all of these modes, and for getting various constants that are not particularly important, I have a square root of qn squared. So I will get a minus 1/2 because of the square root being in the denominator when I put it inside the log. And then I would have log of the magnitude of this wave vector, given that it has these two components, is going to be this q squared plus n pi over h squared. Okay? Now, what I'm going to do is to perform the correct integral over, along the q direction. I notice that since this in principle can be arbitrarily long, this sum over q I can replace with an integral dq over 2 pi, q running from minus infinity to infinity. This q can point anywhere. In fact, in going through this, I better introduce not only the 2 pi, but the length L, because I think that now it is too good. Okay. And then we have the sum over n, which runs over the integers now, of this log. Okay. Okay. Don't ask me any tough questions that I have. All right. So we have to actually now what did I want to do? Let me calculate a force. Actually, let me calculate a version of the pressure, because I expect the force to be proportional to length. And typically, we get pressures by taking the derivatives of log z with respect to the appropriate volume, in this case, the two-dimensional volume, which is LH. So you can see that the L dependence I can immediately get rid of. So now I have to take the derivative with respect to h inside the log. It is h to the minus 2. When I take the derivative, it becomes minus 2h to the minus 3. So the minus 2 and the minus half cancel. There will be one factor of 1 over h, and then n pi over h squared. So that's the derivative that comes from here. I maintain the sum over n that I have to do. I still have to do the integration over q divided by 2 pi from minus infinity to infinity. And having taken the derivative of the log, taking the derivative of this, what I'm left with is q squared plus n pi over h squared. Okay? So now this is an integral that I can do, because I can identify this as something that has poles at q equals to minus plus I n pi over h. So I can complete the circle, use the residual theorem, and this entity becomes, I had the 1 over 2 pi, the residual theorem will give me a 2 pi I, and then I will have twice one of the residues that survives, which is I n pi over h. Okay? So having done that integration, what do I have? I have still the 1 over h that is out front. This will give me a factor of 1/2. I will have one factor of n pi over h that cancels one of these factors. So I will have the pi over h, and then I will have the sum over n of the remaining n. Okay? Which, of course, we now have over here as zeta of 1, which is minus 1/12. So we can calculate this pressure also to be minus pi over 24 over 24 divided by 1 over h squared. Now you say dimensions. What happened to dimensions? 1 over h squared is not a pressure. Of course, the derivative of log z with respect to volume does not give you pressure, but gives you beta pressure. Okay, so pressure is indeed going to be kT over that. Now, this example, I don't know of a physical realization of it. The only reason I bothered to put it for you is because we see that the same entity showed up in both this two-dimensional classical calculation and that one-dimensional quantum calculation. And the reason I wanted to include that is the generality of this result, that calculations for d-dimensional quantums map to typically d plus one-dimensional classical. And so this is one example of that. Okay, now after I go through the next two boards, I will go to the slides and show you experimental realization of the next two things that I'm going to talk about. So to show you that all of these mathematics actually has been done in experiments. The first case is just the previous case, thermal, but something that you can do in 3 dimensions. So now exactly the same thing as before. We have 2 plates that are at a separation h, and we put in between them a fluctuating field with an energy cost that is gradient of phi squared, with conditions of boundary conditions at these 2 points. And the experimental realization of this is if I were to put a superfluid between these 2 plates, because the superfluid has fluctuations in its phonons, and the phonon fluctuations are precisely this. And actually, if I don't go very close to 0 temperature, if I'm close to the phase transition, let's say, of a superfluid helium, I can treat these modes classically. I don't need to go to the quantum case, hence my thermal characterization. Okay, so what do? I just need to do the corresponding calculation that I have over here, increasing dimension by 1. Everything up to here will not change. I will have minus 1/2 L times dq becomes area of the plates, integral d2q divided by 2 pi squared, log of q squared, which is now a 2-dimensional in-plane vector, plus n pi over h squared. Now, unfortunately, in this case, the trick that I had for being able to do the q integral by taking a derivative first does not work, but there is something else that I can do. I notice that this d2q I can write, because of circular symmetry, as 2 pi q dq, and integrate over the radial vector q, which is now scalar 2 pi q. I have to divide by 4 pi squared, which is the square of that. And why that's nice is because the argument of the log depends on q squared, whose derivative is 2q dq. So I can now do the integral n pi over h squared. Now it turns out, and I have, of course, sum over n, and I have here minus 1a over 2 sum over n. And actually, this, what I wrote down, is not quite meaningful. I really should introduce some kind of short distance cutoff or largest wave number, but hopefully none of my important results will ultimately depend on that. Okay. Now, having done that, I can take advantage of the derivative of this being this entity to integrate essentially something that is log x. So what do I have? The pi cancels. I have a 4 pi here becomes 8 pi. So I have minus a over 8 pi. I have a sum over n. I have the integral of log q, which is essentially q squared plus n pi over h squared. The argument times log of q squared plus n pi over h squared. If I want to put an e, I have to evaluate this entity between the 2 limits that I have, which is 0 and lambda. Okay. So what do I have? I have a factor of area. The whole thing has to be proportional to area. I'm a little bit unhappy with my, yeah, where does, Yeah, where did I lose the extra 2? Yeah, the derivative of q squared is 2q dq. That's where. But I still don't like 8. So, I think I made a mistake somewhere. You know what? Let me do it the way that I did over here. So I don't lose. I think I can do it this way, so maybe I will leave it as an exercise for you. But what I did in my notes, which let me follow, is to actually do what I did over here. That is, I calculate the beta p, which is the log z, with respect to now the real volume. Volume is corresponding to A and H, because the advantage of this is that the the A immediately goes away. Okay, so what do I have after I do that? I have 1 over H, same thing that I did before, because when I take a derivative of this, I get a 2, which cancels this, in fact a minus 2. I will get an H cubed, so I will write it as 1 over 1H outside and 2H's here. So that's the derivative of H. And then what I have is the derivative, which brings out the factor of q squared plus n pi over h squared. So it's exactly what I had done before. The only difference is that the integration that previously I had dq indeed becomes 2 pi q dq divided by 4 pi squared, going from 0 to lambda. Okay? Good. Okay, so this now indeed becomes, once I cancel the pi, I told you not to ask me questions. It's my fault. I made the mistake myself. Okay. 1 over 4 pi h now. Indeed, that's correct. The area has disappeared. Now this integral, I can do the q squared with 2q dq. And so the result of that integration is the log. Okay, so this is n pi over h squared. I have to evaluate log of q squared plus n pi over h squared, which is the integral of this quantity between the two limits, which is 0 and lambda. Okay. Okay, so what do I get? I get 1 over 4 pi h, sum over n running from 1 to wherever, n pi over h squared. From the upper cutoff, I get something like log of lambda squared plus n pi over h squared. From the lower cutoff, I get n pi over h squared. Okay. So rearranging things a little bit, what do I have? I want to essentially invert this ratio, so I get a factor of minus. So then I will get a minus 4 pi h. This thing, if I were to just take by itself, is log of n squared, so that will give me a factor of 2 log n. So let me pick out the factor of 2. Here I have a pi squared h squared So the difference between what we had before was that I will get a sum over n squared from here, and from here I will get a log n. Okay? So that's one term. And indeed, from the other term, I will get some contributions. Which I will maintain. I claim that to the lowest order, I will get from here, from the numerator, a term that I won't bother to write, but it's good to know what it does. To the lowest order, it will be lambda, because we are looking at essentially very large cutoff and small lambda, and the corresponding sum is a sum over n squared. Okay? Now, suddenly we encounter two of these series terms that we have to deal with. One of them is a sum over n squared, but that has unfortunately this coefficient that is lambda, log of lambda squared. Fortunately, if you go and look at the tables or do the type of regularization that we did, you find that this zeta of -2 is in fact 0. So we don't need to bother about that, and that's why I didn't write it. Okay. Now we have another entity here, which is a sum over n squared log n. Now it doesn't naturally fall into the form of these zeta functions, because the zeta functions for general integer, for general s, in fact, not even integer, are defined as sum over n of 1 over n to the s. There's no logarithm. Now, it's easy to see how I could get a logarithm. All I need to do is to take a derivative with respect to s. Because when I take a derivative of with respect to s, this I can write as e to the s log n. So the exponent will have a factor of log n. When I take a derivative with respect to s, I will get a log n and then e to the minus s, so n to the s will come back up to a sign. Okay? So you can see that these objects that have logs up to this minus sign can be related to derivative of a zeta function. So it turns out that this entity over here is minus the derivative of the zeta evaluated at -2. Okay? Now, whereas I could, on the board, write for you the expressions and the epsilons, etc., and calculate what this is, I didn't find the corresponding thing, but I found something very much easier that I will show later, that tells you that this object is in fact the zeta of 3 with positive, which is a particular value. It's around 1.2 divided by 8 pi. So at the end of the story, once you do all of these things, you will conclude that the fluctuations in phase of a superfluid confined between two plates will exert a pressure on the two plates, which has the value of 2. Let me just write down the final answer so that I don't make a mistake. Minus zeta of 3, which is around 1.2, it's a number, divided by 8 pi, kt, of course, divided by h cubed. And again, dimensionally, this is force per unit area, energy per 2 lengths to make it area, and 1 length to make it force. So this is something that we will be looking for in experiments, whether this number is correct or not. So you were asking me whether these zeta function tricks, etc., one can confront them with experiments, so we will look at one such experiment. But there is one other experiment that we would like to look at, which is the thing that really started this whole process, and hence the name. Which is the force of an electromagnetic field confined between two mirrors. So this is the case of the three-dimensional quantum fluctuation. So we did already the one-dimensional calculation. We know how to generalize these calculations to other dimensions. So really, I can immediately go and write for you what the expected energy content of these zero-point fluctuations is. Essentially, they're going to be h bar omega over 2. Omega is c times the magnitude of the wave vector. The wave vector is quantized along the z direction, if you like, to have multiples of n. In the two other dimensions, there is no restriction, so I would put it this way, put an area factor. And then what I need to do is to put the modulus of the wave vector that is characterized by q and n. So that is the square root of q squared plus n pi over h squared. Okay. Is everybody happy with this expression? Okay. So all I need to do is to somehow evaluate that. All right. This is actually not bad because we have the q squared and we have here a 2 pi q dq. So I can do the same thing that I did before and do the integration over q first. So I have h bar c over 2. I have pi divided by 4 pi squared. I have 1 over 4 pi. Okay, keep that. I have the sum over n. There's also the area. Okay, so I have the area. I have the sum over n. And then if I were to integrate this object, which is something to the 1/2 power times d of that something, so that becomes something to the 3/2 power. And there's an additional factor of 2/3 that I get out of the integration. This entity has to be evaluated between the two limits of 0 and lambda. Okay? Okay, so let's rearrange some of these things. I have A should be there by extensivity, h bar c necessary by dimensionality. I have a 1 over 12 pi from the combination of all of these objects. And then evaluating that thing, I will get a cutoff dependent part, which is lambda to the 3/2, and a part that is independent, so I will get a minus n pi over h, the whole thing cubed. Okay. As usual, we will ignore these non-universal parts. Okay, so what do we have left? I have a coefficient which is minus a. I have h bar c. I have 12 pi. I have a 1 over h cubed. And then I have a sum over n cubed. Okay, sum over n cubed is something that you can regularize yourself and convince yourself that it is 1 over 120. So the final answer over here becomes plus a h bar c 1440 pi 1 over h cubed, which then converted to a pressure from the E0 with respect to h. Pressure includes some additional factor of area, becomes, first of all, h cubed will get rid of some of this and becomes 480. H bar c 480 pi cubed. Yes, thank you. So this becomes pi cubed over pi, which is pi squared. And this becomes h bar c pi squared over 480 1 over h to the fourth. That was their other mistake. Okay. So we have a pressure that has this form. Actually, I will shortly show you an experimental attempt at calculating this. And you will see in the formula that I compare with, rather than this, I have something like pi squared over 240. And the reason for that is very simple. I did all of these calculations for a scalar field. The electromagnetic field I can decompose into two normal modes, Tm and Te, if you like, because you are dealing with something that has both electric and magnetic components. Each of them gives you the exact same result, and the answer has to be multiplied by 2, and this would be the result of Casimir. Okay, so this is the portion that is the calculation for this lecture, and I was going to show you some results. Any questions? Okay, let's see if this works. Okay, the first thing that I want to point out is that the material that I said notes, etc., exist. You can go to this website and access them. So this particular page is currently actually exactly this website that's downloaded. Okay? Now, the kind of zeroth order outline of lectures is what I have over here. And you can see that I've pretty much followed all of the stuff over here. And what I'm going to do now is to sort of show you some examples of these results for various forms of Casimir forces. And then the notes that were promised in this very ugly Oxford style that was given me compiled so far. And one of the things that I want you to note is that the various things that I told you you should be doing as exercises are indicated in this. And there are 4 of them as you scroll down. The longest one has to do with calculating dipole-dipole interactions, which is coming shortly. And I won't be going over the rest of the stuff after that. Well, never mind. You can find it. Okay, so that's about the notes, and all right. So what I finished with is what I have over here, the calculation that Casimir did back in 1948, essentially following exactly what I had over there. Modes quantized along the z direction here indicated d as opposed to my h. Frequencies omega times the magnitude of wave vector. You do the calculation and you come out with the answer that I have here as a force per unit area, as I said, with a coefficient that is twice what I calculated for you. You can then ask, well, this is a pressure. I know pressure of atmosphere. How does this compare with? You say at what distance? And the answer is that if you go to distances that are of the order of 1 micron, the value of the force that you get is of the order of a fraction of an atmosphere. If I were to go to a tenth of a micron, for example, it would be, a fraction of the an atmosphere of pressure. So it took a while to experimentally confirm these forces, but they have done by now. Before going to the experiment, I noted that actually most of the results of the experiments these days, since they are performed not with ideal boundary conditions, which is what I calculated, but with actual metal plates that have some dielectric constant, etc., through a formula that was given by Lifshitz that takes into account the actual dielectric properties of the material. It's a result that for perfect mirrors will coincide with this, but that separations that experiments are doing typically is of the order of 5–10% different from this. So part of the reason for the discrepancy is the fact that you don't have an ideal material. Okay, so as I said, the force being you need to calculate things that are fraction of an atmosphere at very short distances that are fraction of a micron, had to wait until 1990s, where the apparatus for measuring these forces through atomic force microscopy became available. And then suddenly a whole host of people, originally Stephen Lamoureau and then later on Omar Mohyeddin, did experiments in which essentially they attached a gold sphere that was of the order of hundreds of micron in size to some cantilever, brought it close to a gold plate, and the deflection of the cantilever provided them, they could bounce off a laser and measure it sufficiently accurately, a measure of the force provided they knew the spring constant of this cantilever, which they could separately calculate. And for example, this paper already from 1998, let's see if we can see it. Actually, I had it offline. I don't know why I went to this. Okay. All right, so that's the Casimir formula and things like that. And eventually you can see a comparison of experiments which are these dots with the prediction, which nowadays is much, much more accurately done. And still a puzzle emerges because at the level of few percent, which is far beyond the precision of the experiments, there is a discrepancy between Lifshitz formula and what is experimentally measured. And so that's a puzzle that has remained. But if you are satisfied at the level of a few percent, this formula already works very well. Okay? Now, later on, people were thinking about applications of this to technological things. In particular, there is this term microelectromechanical systems. So by definition, they are at the level of microns. They are dealing with conductors, and they want to move them around. So they are going to be subject to these forces. And if the forces which are attractive cause portions of this device to suddenly stick to each other, you can't separate them, and the device failed. So there was a lot of effort back about 10 years ago, that I will briefly discuss as to whether or not it is possible by some trick to make the Casimir force that is attractive to become repulsive. So at some point we'll discuss that. Okay. Now that was the quantum version of the fluctuations and an experiment that verifies that. What about the thermal version? Well, there was one version of the thermal that I didn't mention to you. In all of the things that I discussed, the field theory that I put between plates was this free field theory gradient of phi squared. Now you can ask whether in, say, liquids, active matter, etc., where do you get closest to that kind of theory? And the characteristic of that theory that I mentioned to you right at the beginning was that it had infinite correlation length. So what you want to do is to go to a system, if you are dealing with a fluid that has an infinite correlation length, so you can get that at the critical point. And visually, if you have a system at the critical point, you will see critical opalescent, all kind of long wavelength fluctuations. The actual experiment was actually performed by, before going to the experiment. In the 1978, Fischer and Dejean proposed a consequence of having a fluid at the critical point, and the consequence was that you will have the analog of these pressures that we discussed, except that the fluctuations that we are dealing with come not from an infinitely long-range correlated free field theory, but the theory that comes by being at the critical point. But as far as calculating, say, the free energy, force, pressure, etc. is concerned, all of the dimensional arguments that we gave holds. So there is a contribution to the energy. Energy has to have dimensions of kT. It has to be extensive, so it has to be proportional to area. But I already made the dimensions to be energy, so I have to get rid of those areas. The only length scale that I have is the separation h, so I divide by h squared. So it's exactly the results that we had before, actually underneath that board itself. The only thing that we don't know is what this amplitude is. So the amplitude we got through these calculations, zeta function, etc., by tricks that were relevant to the free field theory. For this interacting field theories, calculating this amplitude amounts to calculating something like a critical exponent. And calculating critical exponents is in general a difficult business. But what do you care? I mean, it's some number. All of the other parts of it are exactly correct. So this prediction of Fischer and Dejean was experimentally verified in 2008 by the group of Bechinger in Stuttgart, where the critical point that they created was not that of a liquid-gas system, but rather was a mixture of oil and water. So if you mix oil and water, there is a regime where you have separate droplets of oil in water or water in oil, and then you have a point where things start to get mixed and you have coexistence, and the coexistence interval terminates at a critical point in which the droplets, if you like, have all kinds of sizes. Correlation length has gone to infinity, so the prediction of Fischer and Dejean should be equally relevant to that point. And so what they did in experiments was that they actually had spheres. If you remember, the quantum Casimir force was also measured between a sphere and a plate. We will go into the distinction between two parallel plates and sphere and plate later on, but ignore that for the time being. So you had a colloidal sphere in a mixture of oil and water, and the bottom surface was glass. They could shine a laser, which partly was evanescent wave that was going into the fluid, but enough of the evanescent field went into the fluid that it could light up the position of the colloidal particle. So what they could do is to follow the height of this colloidal particle that was performing these fluctuations. Okay? Fluctuating quantity, you can say, oh, these fluctuations are coming from the Boltzmann weight of some potential that is acting between the colloidal particle and this. So if you have sufficient data such as this, you can convert it to a probability distribution, take the log of the probability distribution, multiply by KT, and you get the interaction potential of the colloidal particle with the underlying glass surface. Then what they do is they change parameters such as temperature so that the fluid in which this colloidal particle is fluctuating up and down goes through the critical point. Okay? And away from the critical point, correlations are finite. So the sphere really doesn't know through the fluid fluctuation that the plate is there. So there really is no, or at best some short-range interaction. But you reach the critical point, you have these correlations that have gone to infinity, if you like, islands of all kinds of size. And so suddenly the colloidal particle knows where the plate is and experiences this long-range fluctuation in the induced force. And so what they do is they plot what happens to the effective potential as they tune in close to the vicinity of TC. And right at DC, they see that this long-range interaction due to fluctuation suddenly emerges and is in very good agreement with the appropriate generalization of what we have been discussing to that case. Okay? Yes, any questions? Very nice experiment. So you can see that essentially experiment has been running behind theory by 30, 40 years in this field. Okay. Now the calculation that is now hidden behind this was what I mentioned that we could do not only for a critical object but for a superfluid. So what do I mean by this? This is a very nice experiment that was done by Moses Chen at Penn State University. So what they had was a bath of liquid helium. On top of that bath, you suspend a copper plate. Okay? Now, some of the helium actually jumps ship, leaves the liquid, and forms a wetting layer on top of this copper plate. Why does it do that? The reason for that is that helium is very weakly, because of weak van der Waals forces, attracted to itself, but much more strongly attracted to copper, because typical strength of van der Waals interaction is proportional to the product of the atomic numbers. The atomic number of copper is certainly much larger than helium. So the helium, by leaving here and going here, is gaining attraction by being close to this. But it is paying a cost because it has to overcome the gravitational potential cost of going all the way up. So because of the gain from the attraction to the copper versus the loss from the gravitational potential, there is a particular thickness of the film that emerges, and that thickness of the film is a measure of the strength of the van der Waals attractions. So if you add up all of the van der Waals attractions, you find that the interaction of a film of thickness d, the gain that you have falls off as 1 over d squared. Whereas the cost to move this all the way up here over a distance h, a film of thickness d, is proportional to the thickness and how far you have to go. So this expression combines the loss of gravitational potential energy and the gain in van der Waals attraction. And if I balance those two terms, minimize that expression, it tells me what the thickness of this film should be. So everything about this van der Waals constant has been known experimentally for a very long time. So you should be able to predict the thickness of this film. Okay. Now what they did was, okay, so you figure out what the thickness of this film is at room temperature, at whatever the relevant temperature is, and then you gradually pump out helium so that the whole thing becomes lower and lower temperature. So essentially, you go down this coexistence curve and you continue to measure the thickness of the film. You would say the strength of the van der Waals attraction should not really vary very much as a function of the thickness of, as a function of temperature, so the thickness of the film should not change. And indeed, this is what they find, is that the thickness of the film at high temperatures, high enough like 4 degrees Kelvin or whatever, is essentially staying constant. So they have set that constant to whatever it is in this. They have set it to 0. It doesn't matter. The point is that it stays constant. Now, as you are cooling this helium, suddenly you undergo a transition over here. And then Fisher and Dejean predict that once you are at this point, you have these critical fluctuations that take place, and the critical fluctuations give you an additional contribution to the free energy, and that, as we have been calculating all along, scales also as 1 over d squared. Okay? So you would say that right at the transition, suddenly, because of the critical fluctuations that appear, this coefficient changes, and so the thickness of the film should be modified. And indeed, what they see is that once they hit the transition, whoop, the thickness of the film suddenly changed. Okay, the film became squished, if you like. And so you say, okay, once you are away from the transition, then the correlation length again becomes smaller, and so this term should vanish, and the film should come back to where it was before. But you can see that it doesn't. It doesn't go all the way back to the level that it had before. So you can ask what happened. Well, we've done part of the calculation. We said that once you are within the superfluid, you have this additional degree of freedom, which are the phonons of the superfluid, that can create these long-range interactions. And because of the phonons of the superfluid, the two parts of the surface can know about each other and have some kind of an interaction between them. And so there is a corresponding Casimir-like force, not because of critical fluctuations, but because of the phonon modes of the superfluid. And therefore, this should go back where it is. Okay? Now, exactly this number that we had before with the zeta of 3 divided by 8 pi, etc., should then tell us what the difference in thickness between the two sides of the transition should be, because that's the additional component of the force that you put on. And you do that calculation and you get this dashed line. Okay? So that bothered us, because it seemed to be about 3 times less than it should be, what we had calculated. So there is something else. We are wondering either all of this is not correct or something we are missing. And the thing that we eventually decided we are missing, okay, so this is the calculation that I did on the board with the zeta of 3 for pi, or all of those things, and that wasn't enough. But then we said, okay, this is not the geometry that we did the calculation, because the film that is sitting over there, on one side it's fixed by the copper, but on the other side it's air, and it can have capillary fluctuations itself. And the spectrum of the capillary fluctuations in a fluid is such that it's like the gravitational waves. It knows about the depth of the fluid. So you calculate what the cost of those fluctuations is, and it gives you a contribution to the free energy, which is exactly of these forms that we had before, up to a factor of 7/4. So there is roughly twice on top of what we calculated from phonons because of the capillary mode fluctuations. And so once we add that to that, we predict that it should really come down to this level, which I think with the level of the experimental precision and what we have so far is not bad. So because because it is the presence of the superfluid film that allows the fluctuations on the surface to know about where the bottom is. And once you don't have the superfluid, you do the corresponding calculation, you don't get that. It's a, if you like, a short range effect. There is a damping that goes on that you don't have in the superfluid. Yeah. Okay. Okay, so we see that there are indeed experimental realizations of what we've been talking about. And so finally, I wanted to sort of say that this issue of fluctuation-induced forces, they come in many different contexts. And one context that people have been talking about, somebody mentioned the mattress effect, which was non-equilibrium, but there is something that is kind of reminiscent of that, which is that if you have a surface, I mentioned just now capillary modes, but you can think of a soap film that has thermal fluctuations of its height, and because of that, it is moving around. And you could, in principle, imagine that you put objects on the surface that modify or damp out these fluctuations. Then there should be some corresponding fluctuation-induced force between them. As far as I know, there have been predictions of this, including by us and Ramin Golestanian, who comes some time from now, back more than 25 years ago. Nobody has been able to sort of experimentally demonstrate that these forces exist. More recently, this group, Mahta, which Jim Setna proposed that for actual membranes that are kind of clean version of what we have in our red blood cells, it's a mixture of two lipids, and the two types of lipids tend to phase separate and form domains. And the claim is that this two-dimensional version of the liquid gas oil-water separation that I mentioned, so we looked at the three-dimensional oil-water separation, this would be the two-dimensional version of it, that for some reason or other, life has conspired to be close to the critical point, so that there are long-range interactions between proteins that are embedded in this fluctuating composition field. Now, the interesting thing is that in this two-dimensional case, what we are dealing with is the Ising critical point. And so whereas when we were calculating free field theory correlators phi of x, phi of 0, they were this simple power of x to the power of d minus 2. When you are at a critical point, this phi of x, phi of 0 is going to be governed in its fall-off by an anomalous critical exponent, typically labeled by eta, so that the typical interactions also are governed by this non-integer power, if again a clean realization of this system could be found. Okay. Any questions? All right. I guess I have another half an hour, so I may as well start on next lecture material. Yes. 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 Exactly. Yes. Yes. Right. It's just that it is much less clean. And so what they had to compare with were typically things like epsilon expansions or computer simulations. The good thing about being at the critical point, and maybe something that I should emphasize again and again, or having infinite range correlations, is that you get to have universal concepts because things average out. If you are, however, there are many, many more examples of fluctuation induced forces which are short range. The most important one in the active matter community is probably the depletion forces. And there, the size of the force, the range of the force is the size of the depletant. And so that's, then you can see immediately how non-universal it is, how it depends on shape and things like that. Yes. Okay, so the calculation that I did over here implicitly assumes that this dimension is much larger than the other one. People have done computation for things like cubes and rectangles or whatever, where the ratio of dimensions is finite. And indeed, then rather than having integral in one direction, you have to do sums in all directions. And some unusual things do happen, like the sign of the something changes sign, etc. And I'll come to some of those effects later on. I will mention some of those things. Yes. Well, I mean, the extra dimension is some kind of an imaginary time, if you like. You have to perform some kind of a transformation that takes you, let's say, for the simplest case of a single particle quantum mechanically described, if you want to go through the Feynman path integral, then you have the sum over paths. The length of the paths or the direction is not necessarily time, right? It is just one additional dimension that you have to look at. But it is the same transformation that is at play, that you have the usual classical x coordinate, you have to introduce the corresponding conjugate momentum coordinate, which quantum mechanically they don't commute with each other. And one way of getting rid of that non-commutation is to go to the other direction and do path integrals. Okay. Okay. So um, I had a one-dimensional quantum systems. This one-dimensional quantum system had these fluctuations that were confined between the distance 0 to h, right? Now, if I were to make a corresponding path integral for that, essentially I have to construct some kind of action in which each of these fluctuations is allowed to proceed in this, as you said, kind of time-like direction. Okay? And calculating, let's say, some kind of a partition function in two dimension for the one-dimensional case that at long times gives you the energy times time, because it's what you are doing here is constructing some kind of action, so you'll have energy times time. is equivalent to calculating a fluctuating field in this two-dimensional space, whose partition function is going to be proportional to this length over here. So you have to divide by the length here, so that's why we had a pressure for the two-dimensional case that could then be made an analog to the force that was taking place in the one-dimensional quantum case. Okay? Anything else? Okay, so let's proceed with this kind of dimensional analysis. So I have been focusing so far on why these amplitudes are important. For a while, I'm going to even forget about the amplitude and just do the dimensional analysis. And so let's do the dimensional analysis for some object. I drew it like a sphere, but it could be any object that has some characteristic dimension A. And I bring it next to a surface. And so there are, actually, I had this nice experiment of the colloidal particle close to a glass surface. And actually, part of the interaction, even if I were to sort of completely ignore the fluid, is the direct electromagnetic interaction, van der Waals interaction that you would have between the colloid and this object. Although in that case they also had some charge, but let's forget that. So if there's no charge and both of these objects are neutral, then really the electromagnetic fluctuations that I have to deal with is when there's a excess of plus charge that has appeared shortly at one end and disappeared. So there's a dipolar fluctuations. And typically there is a cost for creating a dipole fluctuation that is proportional to strength of the dipole p squared and has a coefficient which is the polarizability and the polarizability is proportional to volume and things that depend on the dielectric constant. Actually, let's begin by not thinking about the interaction between particle and plate, but the interaction between two particles. Let's say this has dimension A1 and this has dimension A2. Again, they are neutral, so the only way that they know about each other is because of the dipolar fluctuations that you allow in each one of them. Okay? So since the dipolar fluctuations are everything, the answer has to be proportional to the product of the polarizabilities, and dimensionally it has to be proportional to the product of the volumes. Okay? So how does the interaction look like as a function of separation? That kind of depends on what is causing the fluctuations. So one of the things that we said was maybe it is due to thermal fluctuations. If it is due to thermal fluctuations, then the energies are characterized by kT. But I already took care of energy, so I better get rid of the powers of distance that I have over there. And the only thing that I have to get rid of that is the separation between them. So I have to divide by 6 powers of the separation. Okay. But what about quantum? So for the case of quantum, we saw that again, h bar has to be there. And since the appropriate fluctuations are the electromagnetic field, the speed of light better appear in the story. It is again the polarizabilities that are the relevant quantities. But h bar c compared to kT has some additional power of length So this is going to be r to the 7th power. Okay. Now you can see that which one of these wins depends on how r stands with the quantity that I call lambda t, which is obtained as a ratio of h bar c over kt. So there is a thermal de Broglie wavelength that for room temperature is around 8 microns. And it is at larger distances that I will see the thermal effect, and at shorter distances that I will see the quantum effect for interaction, let's say, between two molecules. Dielectric constant, yes. Now, typically, these large distances of 8 microns or so are too big for having to worry about any appreciable interaction between atoms or molecules. So we are not typically interested in this regime. But this r to the 7 you may have remembered as something that is called the retarded van der Waal. Okay. And this r to the 6 is not the van der Waal. Okay. There is a true van der Waals interaction which falls off as r to the 6th to compensate again polarizabilities that are like this. But if you did calculation of van der Waals in your quantum mechanics, you typically had two atoms that had excitation level. There was ground state, and then there was the first excited state. And when you did the matrix elements and did all of the calculations, you'll find that the answer actually does depend on resonances and excitation frequencies of the molecules. Okay. So that's the true van der Waals interaction. And the transition between van der Waals and the retarded van der Waals, which in some sense is less blind, it's more blind to the details of what is happening with the molecule. So as you go to larger and larger separation, you see less details about the structure of the molecules. You go to this more universal retarded van der Waals limit, and the separation between them depends on what this is, and this typically occurs, let's say, around 20 nanometers for hydrogen. So you have this set of interactions, all of which we can kind of get from dimensional analysis, that are these important fluctuation-induced interactions that are really holding pretty much most of the things that we see in the world around us, sort of emphasizing the importance of these fluctuation-induced interactions. Now, let's go to the geometry of a particle that is approaching a plate. Again, let's call the distance h. And this is sometimes called Casimir polder, because shortly after Casimir published the paper on Casimir forces, he did this calculation for a sphere in front of a plate. But again, that's an idealization. You can ask what the analog of all of these things is, and again, we can use dimensional arguments. That is the U of thermal. Let me, in this time, write the forces, just to make sure we distinguish between forces and potential. Again, however, I have KT. It is proportional to polarizability. I have to get rid of length scale, so I have to divide by actually 4 factors of h. 3 of them to get rid of the a cubed, and the other h to make kt over h into a force. And then again, I will have the analog of a retarded van der Waals regime, which would be h bar c a cubed h to the fifth. And eventually I'll come back to the usual van der Waal, which would be dominated by resonances a cubed h to the fourth. Yes? Okay. So typical argument that people have is that when you do your calculation in your standard quantum mechanical class, where you have two atoms or molecules that have some excitation, and you calculate matrix elements corresponding to the dipole-dipole interaction, you get this answer of 1 over r to the sixth. And then you say, well, this is not quite right, because it assumes that everything is instantaneous, but the interaction between two dipoles, really, if they go far apart, I have to worry about the travel time of the light between the two objects. And so if you sort of make appropriate comparison, also the distinction between these two regimes comes according to how the separation is related to the travel time of light from one to the other. And so basically, retarded is because by the time the influence of the dipole went and came back, there was time for the dipole to move to some other location. Okay, so you have this set of things. Now, this is all to justify the following, that all of this is also, by the way, valid in this case for R has to be much larger than A1, A2. In this case, H has to be much larger than A, so that focusing only on the dipole fluctuations is enough. So the point is that if you have something that has charges and has net charge, and you're very far away from it, the only thing that you see is the net charge. However, if its net charge is 0 and it's very far away, the thing that you see is its dipole. As it comes closer, in addition to the dipole, you see that, oh, in addition to the charges being like this, maybe there was an additional small charge over here, so you start to see quadrupole and higher order multipoles of the interaction. So as I bring this object closer to this, just looking at it as a dipole fluctuation becomes less and less applicable, and I have to look at all kinds of things that are going on. And so one thing that maybe one can ask is, suppose I have a gold sphere and a gold plate. If I'm very, very far apart, I have this dipole, and I know exactly what it is. When I'm very close, I have this sphere, and this separation is much less than the radius of the sphere. Essentially, I see something that is very much like parallel plates. And so there I can use the Casimir type of approximation on top of something that I will discuss next time around. It's called proximity force, to calculate what that force is. It is the in-between stuff that is most difficult, and you don't know what to do. And part of the reason it is good to emphasize is that these fluctuation-induced forces are not pairwise additive. So you may be tempted to say, okay, I know the van der Waals interaction between every atom and every other atom, or every molecule and every other molecule. Why don't I add them all up? And that would be the net force, and that's incorrect. Again, the reason it is incorrect is if we sort of trace back all of the calculations that we have done, you say that these fluctuation-induced forces are inherently dependent on the distribution of these constraints all over the place. And so how we sort of go from this limit that we understand to this limit that we can reasonably approximate is an interesting question, which I think I'll start talking about next.